Today I'd like to discuss about the interfacing of memory and then after IO devices with 8085, how to interface the memory devices or IO devices that would like to be discussed. So the first, I think all of you know familiar about the RAM and ROM concept. So what is it? The program and data that are executed by the microprocessor that have to be stored in ROM or and RAM, which are basically the semiconductor memory. Okay, the program and data that are stored in ROM that are not erased even when the power supply is removed. Okay, and that's why this ROM is called the non-volatile memory. It can be used to store uh, permanent programs, like as for example monitor program, um, which is called as startup program, and data. Some lookup table has to be stored, which are very important or necessary in microprocessor based system. Now the difference between ROM and uh, EPROM. EPROM means erasable programmable read-only memory. Okay, so what is the basic difference between ROM and EPROM? The ROM chip that can be programmed only once. Okay, but in case of EPROM chip, that can be programmed many times after uh, erasing the previously stored contents. And how this previously content can be erased? Using the UV rays. Okay, by passing the UV rays uh, for a few minutes through the quartz window mm, situated at the top of the IC, and after that the previous data can be erased. Now what is RAM? In a RAM, stored programs and data that are erased when the power supply to the chip is removed, and that's why the RAM is called the volatile memory. Now programs and data which are often uh, stored in the RAM that are modified, that can be modified. Okay, so for example, uh, what you need to do with the microprocessor, what is the programming, the concept that your program should be stored inside the RAM, which can be altered anytime. Okay, so example of such programs and data include programs written during software development for a microprocessor based system. So programs written when uh, one is learning assembly language programming, and data entered while testing these programs. Just as in case of you have to use the programming concept to do the practical classes, whether it is used by the trainer kit or the simulator. Okay, so RAM is also used to store data that are variable in nature. For example, data that is to be uh, used to store uh, that is used by the programmer by you for arithmetic and logical operation, that can be stored in the RAM. Okay, and data can only be read from a ROM or EPROM, whereas it can be written into the and read from a RAM. So now the interfacing of EPROM or RAM, the memory devices with the 8085, that can be performed using that can be connected via decoder circuit. Okay, decoder. And how this decoder can be made? Decoder can be constructed using logic gates, and this decoder IC, which is called the 74LS138, that must be connected to interface any memory device with the microprocessor 8085. Okay, so move on to the next slide, where I need to discuss about the interfacing of memory chips with the 8085. Now 80, since this 8085 has 16 address lines, which is A0 to A15, as you have seen in the architecture, a maximum of 64 kilobytes of memory locations can be interfaced with it. And how this 64 kilobytes is calculated? Using the number of address lines, 2 to the power 16. Okay, 16 is the number of address lines. The memory address space of this 8085, that is the range of memory addresses that can be addressed by the 8085. It is from 0000H to FFFFH, okay, when represented in hexadecimal form. All these are hexadecimal number systems. So 0000 to FFFF, okay, and this H represents a hexadecimal number system. Uh, while executing a program, the 8085 microprocessor needs to access the memory regularly to read the instructions and data and to store the different results. Okay. Now the 8085 initiates a set of signals such as IO/M bar, read bar, write bar. Okay, and when so these signals can be initiated when it wants to read from or write into the memory. Similarly, each memory chip, it has some specific signals like CE bar, CE bar, or CS bar, means chip select or chip enable. There is a pin called chip enable or chip select pin, okay, for every memory device, whether it is a ROM or RAM. And for output purpose, there is a pin called OE bar or read bar, output enable or read. OE bar means output enable and RD bar means read operation. And for write purpose, there is a pin called write enable, WE bar, or simple write bar. Okay, so in case of ROM, there are only two signals. One is the chip enable or chip select signal, and the output enable or read bar signal. But in case of RAM, it has three signals like chip enable or chip select, then output enable or read bar for read operation, and for write operation, write enable or write bar signal. Okay, and one thing you have to remember, the memory interfacing circuit, it must match the processor signals to the memory chip signals. In this way you have to interface. Now after that, you have to familiar with the concept of how the control signals has been generated, how the memory read and memory write control signal for memory can be generated. So there are three signals. We have already familiar with these three signals: IO/M bar, read bar, and write bar. Now when this signal is 0, means it's a memory related signal, because M bar is there, low level signal. If this pin has low level signal, it represents it's a memory related operation. If this pin is high, then it reflects the IO related operation. Okay, so for memory purpose, for memory operation purpose, this pin should be low always. Okay, and whether it's a read operation or write operation, that must be reflected by these two control signals. So if read bar signal, read bar pin is low, then it is a read operation. At that time, write should be disabled. And when this read bar signal is disabled, write should be enabled. So that when 001 these combinations are there, that means the 8085 reads data from memory. It may be from RAM or it may be from ROM. But when these three signals varied from this one to 010 this position, then this 8085 writes the data into the memory, which is obviously a RAM. Okay, so when the 8085 wants to read from and writes into the memory, these three signals are needed. Now, using these three signals, IO M bar, read bar, and write bar, these three signals, two control signals are generated. And what are these two control signals? Memory read and memory write. It is seen in this picture that using these three signals, two control signals can be generated. One is memory read, another is memory write. Now, how this memory read signal can be? So when this IO M bar signal, it is connected to a NAND gate via this inverter, and when this read bar signal is to be connected to that NAND gate using the inverter circuit. So that means when this initially gets 0 0, it will be 1 here in this position, and we know that the output of any NAND gate will be low if all the inputs are high. So if both are 1 1, the output will be low. So what will be the signal? The combinations of this one and this one, it will be memory read signal, which is generated over here. And for memory write signal, in the same way, the IOS less M bar, this signal must be fed into another NAND gate circuit, and this write bar signal is to be connected via this inverter to that NAND gate input, so that the input of this NAND gate will be high and output will be low, where this memory write signal is generated. Okay, so these are two control signals. Basically, those are needed to read any data from the memory or any data writes into the memory. Is it clear? Tell me. Clear up to this much? Any doubt? Is it clear?
Yes, sir.
So when this IO/M bar signal is high, both memory related control signals are deactivated, irrespective of this read and write operation, and that is in case of IO operation. So I would not discuss right now about the third condition. So what we need to remember, that means that is the IO/M bar is 0, read bar is 0, write bar is 1. That's why the memory read signal is generated. At that time, memory write signal is deactivated, which is called the memory read operation. In the same way, for the next variation 0 1 0, at that time the memory read signal gets deactivated, but memory write signal is activated, and it's called the memory write operation. Now coming to the move on to the next slide, where the uh, pin diagram of a RAM, or sorry, of a ROM, which is called IC2764 EPROM is there, and these are specified using this type of structure, 8K cross 8. Okay, 8K cross 8. 8K cross 8 means the first thing, that is 8K, it is the size of this IC, means it is a 8 kilobyte EPROM. 8 kilobyte EPROM, that means 8192 locations are there. Is it clear? Now the second 8, it represents the maximum number of bit that can be stored in each memory location. What is the maximum number of bit? 8 bit. So maximum 8 bit of data that can be stored in each memory location. So first 8K, that represents the size of that device, and second 8 represents the data bit size which will be stored inside that memory location, each memory location. Okay, so this is 8K cross 8. Now for another IC, it may be 8K cross 4, it may be 16K cross 8, it may be 4K cross 4 or 4K cross 8. So always you need to identify that the first thing would be uh, represented for size, and second data that must be used to reflect the data bit size which will be stored inside each memory location. Okay, so there are 8192 locations available, and the number of, so how this 8K is to be defined. 8K is represented by 2 to the power 13, 2 to the power 13. Okay, so 13 is the number of address lines those are available for this memory IC, and 13 address lines means from A0 to A12. Okay, 13 address lines represents from A0, A1, A2, A3, 4, 5, 6, 7, then 8, 9, then 10, 11, then 12. These are 13 address lines. Okay, so uh, A0 is the least significant bit of the address, and A12 is the most significant bit of that address. Now they are used to select memory locations in the IC during the memory read operation. Okay, and how can you select the memory particular memory location, that will be discussed after this slide. Okay, now there are some steps that are executed by the 8085 to read the contents of the memory location in an EPROM IC. Okay, the first one is the address of the memory location from where data has to be read is placed in the address bus of the EPROM. Then second is the CE bar signal. Here its bar is not mentioned here. It's wrong written. So you have to consider it is a CE bar. Okay, so CE bar signal is made low, that is 0, and after that it will be activated, because if anything you need to connect with microprocessor, suppose these are the ICs, this ROM and ROM, everything, these are the ICs, but that that IC, it is an EPROM IC, but this IC it should be enabled first, then you need to perform anything using this one. So every IC needs some supply, they need some signal to activate, to enable. Okay, after enabling this IC, you can perform the actual operation. So before enabling or before selecting that IC, that's why this CE, this signal is there. Chip enable. This is an IC. This is a chip. So without enable this chip, you can't do anything, any operation. Okay. So your first thing is to enable this IC, and how this can be made using this CE bar signal. Then OE bar signal is made low if you want to read something from this device. OE bar means output enable. Okay, through which the output must be connected, and this read bar signal is to be connected with the read bar signal, memory read signal of the microprocessor. Okay, so everything will be connected to both of them, processor as well as this device. Now after this, the data in the selected memory location is available in the data lines, which is from D0 to D7 of the EPROM, and after that the 8085 reads the data in the data line. Okay, so the total memory size that can be connected with one microprocessor IC, that is 64 kilobytes long. 64. Okay. Now, among the 64K addresses that the 8085 can handle, some are assigned to EPROM chips, while others are assigned to RAM chips, depending on the um, requirements of the 8085 base system. But normally, a block of address starting at 0000H is assigned to an EPROM chip in 8085 based system that contains the monitor program. Okay, you have to remember this. Normally, a block of addresses starting at initial position 0000. Okay, 0000 that is assigned to an EPROM chip in 8085 system. Okay, you have to write it down. If you have any pen and paper with you, you can write it down, that a block of address starting at 0000H is assigned to an EPROM chip in the 8085 based system that contains the monitor program. Normally, starting location is to be assigned to the ROM IC. You have to remember this. This is very important. Now, this is done because after the 8085 is reset, it fetches the it fetches and executes the instruction that is stored in the address 000H. Okay, and that is the location which program counter points to after the 8085 is reset. Okay, so why this is assigned to the EPROM chip, this starting address 0000? Because after the 8085 reset, it fetches and executes the instructions that is stored in the address 0000H. Okay, while this address should be given by the program counter. It points by the program counter when the 8085 is reset. Okay, so if it is memory locations are, if the memory locations are given in this way, this is the starting memory location 000000. So all 13 address lines are available as 0 for this IC, particular this IC, not for the 8085 microprocessor. Okay, so don't confuse with this one, because this IC has only 13 address lines. So that 13 address lines is given in this way, written in this way, from A0 to A12, and the starting address should be all 0. All bits should be 0 of the address lines, and the last address should be all ones, 1111111111. So this is the variation from all zeros to all ones. In between, how many memory locations are available? 8,192 locations. But you don't need to consider in between these memory locations. You have to consider only the initial location and the last location. Clear? You have to consider only the initial location and the last location. Don't need to consider the second location to the 8,191st location. Okay, only remember the first one and last one. Clear? So this is okay. Now you must clear this concept. If this problem, if it is solved, then you must clear this concept. So write down, or you can listen carefully about this problem. Like, suppose there is a problem statement which is given over here, like interface a 27128 EPROM, which is 16K cross 8 in size. So EPROM IC that with the 8085 such that the starting address assigned to the chip is C000H. Okay. So before executing this one, I would like to say something. While the 8085 has 16 address lines, the number of address lines in EPROM chip depends on the storage capacity of the IC, as I have told you earlier. Now this memory interfacing, this RAM and ROM, that can be performed by two ways. There are two methods to implement this memory interfacing. Either first method, either you can use the logic gates, means NAND gates are available. There are some NOT gates. So inverter, using an inverter, using a NAND gates, you can interface the memory device with the 8085. Second method is to use directly the decoder IC if you want to connect more than one memory device. Like here in this problem, you have to connect one 27128 EPROM IC with 8085. Now if the statement, if this will be like interface two numbers of EPROM IC with one microprocessor 8085, in that case it is better to consider the second method, which can be implemented using decoder IC, because in decoder IC there are some inputs, and based on that inputs one output will be enabled at a time, like 2:4 inputs, 2:4 decoder. Like there are two inputs, four outputs are available. You can maximum connect four output devices with this one. So based on the combinations of two inputs, any one will be enabled, any one output will be enabled at a time. But you can connect maximum four number of devices. Or if you can use the 3:8 decoder also. So it has three inputs and eight outputs. So for to connect more number of memory device with one microprocessor IC, it is better to consider the decoder ICs. But if you want to connect a single device, single memory device with the microprocessor IC, you need to connect using it logic gate. Okay, because for designing such type of system, you have to consider the cost. You have to minimize the cost. Okay, as well as the circuit complexity. Okay. Now, to solve this problem, interface a 27128 EPROM IC with the 8085 such that the starting address assigned to that chip C000H. How can you connect it? Before, so first you have to consider this type of pictorial representation, which is called memory mapping. Okay, first you need to draw this memory map. Then this memory map should be converted into a diagram format, which is look like this one. That is called the interfacing diagram. Okay, but before making it, you have to calculate the memory mapping. You have to use the memory mapping technique to calculate the starting address or ending address of that particular device, because in your problem statement it is given that the starting address is C000. So here you don't know what will be the ending address. You have to calculate it. Okay, so any one address is to be given in your problem statement or design statement, either starting address or ending address. If starting address is mentioned, then you have to calculate the ending address. If ending address is there, then you have to calculate the starting address. Okay, so here we have to calculate the ending address first using the memory mapping technique, and for that one, For that one, you need to write all of these address lines of microprocessor, like A0, A1, A2. How many address lines are there? 16 address lines. A0, A1, A2, A3, and all the way up to A15. The 16 address lines are for microprocessor. Now, how many address lines are available for this device, for this memory EPROM device? Only 13 address lines. So that means, sorry, not the 13 address lines, 14 address lines, because it is 16K. 16K means 2 to the power 14. 16K means 2 to the power 14. So how many address lines are there? 14 address lines, and that must be selected from A0 to A13. A0 to A13. These 14 address lines must be connected with both, with the microprocessor as well as with the device, memory device. Okay, so A0 to A13, these address lines must be connected with both of these devices, microprocessor as well as with this ROM device. But what about the remaining address lines? Because this EPROM device has not the any extra address lines, only it has maximum 14 address lines, but microprocessor has two remaining address lines which are not connected to this memory device, but you can't left open. That's why that's why it will be remain same as it is. Like, the starting address is given in your problem statement is C000. C means you have to write it in binary form. This C000 which is given here, this C000, it is in hexadecimal number system. If you convert it into binary form, then it will be 1100. That means C, then 4 zeros, it is 0, then again 4 zeros, again 0, and again 4 zeros, again 0, which is C000. Okay, now make a separation line between them. That is, these address line must be connected to both of them. These two address lines are extra address lines for microprocessor. So you have to separate them using this dashed line. Okay, now from A0 to A13, these lines are connected to both of these devices, so that's why both can be varied from all zeros to all ones. You have to write it in this way. So all these are 0, 0, 0, 0, 0, 0 up to this one. Then the last will be all ones. In between, how many memory locations are there? 16 kilobytes memory locations are available, but you don't need to consider. As I have told you earlier, you have to consider the first one and the last one, because you have to calculate the ending address. Okay, so starting address is given over here C000, but what will be the ending address? Ending address should be calculated in this way. First, write down the starting address in binary form, then make a separation line, dash lines. Then the address lines, those are only connected with both of these system, that can be varied from all zeros to all ones. Okay, and remaining address lines are not connected to both of them. These are only applicable with microprocessor 8085. That's why it will be remain same from the initial to the last one. And initially it was 1 1, that's why up to last one it will be 1 1. So from these combinations, you can easily calculate the ending address of this device. And how can you calculate the ending address? Take the 4 binary numbers for one hexadecimal digit, which is 1111. In hexadecimal, it is F. Then 1111, again F. Then again take 4 ones, 1111, next F, and then last 4 1, it will be F. So the ending address will be F, 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 F. The starting address was C000, ending address will be F, 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 F. Okay, so this is 16 kilobytes memory location range. So in this way, you have to calculate the ending address if starting address is given, and if ending address is given, you can easily calculate the starting address. How? Listen carefully. If ending address is given, assume FFFF is given. Okay, so write down this FFFF in binary form. Here 11111111. Make a separation line, then those address lines which are available for both of them can be varied from the last ones to all zeros and make them 0 0 0 0, write down 0 0 0 0 0 0, all this about this 14 address lines. Okay, so your remaining address lines will be same for all positions, so it will be 1 1, so take that 1 1 and you can easily calculate the starting address of this device, which is 1100, then it will be C, then 0000 it will be 0, then again 0000 it will be 0, and the last 0 will be 0. So that is the starting address and ending address. In this way you can calculate any one address if another is already mentioned. Okay, is it clear? Tell me, do you have any doubt? How can you calculate the ending address or starting address?
স্যার বলছি যে এখানে স্যার একটা জিনিস কনফিউজ হচ্ছে যে এখানে 13 মানে আমার 2 টু পাওয়ার 14 হচ্ছে গিয়ে আমার অ্যাড্রেস লাইন ছিল
14 address
সেখানে
lines,
আমি
14 address lines.
হ্যাঁ ম্যাম স্যার সেখানে আরো দুটো অ্যাড্রেস লাইন যেটা নিলাম এক্সট্রা অ্যাড্রেস লাইন, তো এটা কি
Okay, these are the address lines for acha ke জিজ্ঞেস করছিলে?
স্যার আমি জিজ্ঞেস করছিলাম স্যার।
Okay, so is it visible?
হ্যাঁ স্যার।
Now take this one is your microprocessor 85. This is the EPROM device. Okay, it has 16 address lines from A0 to A15. It has only 14 address lines from A0 to A13. Is it clear? So A0 to A13 will be connected to both of them, but it has extra 2 address lines. It cannot be left open.
Yes.
So what will be the position of that one? So any we know that every memory address is 16 bits. It is represented in 16 bits. Okay, it is not represented in 10 bits or 11 bits or 12 or anything else. It will be 16 bits. So it is represented in 16 bits form, which is C000. Now you have to consider here all of these address lines, but you have to make the separation lines because some of these address lines are connected to both of them. Remaining address lines are only available for microprocessor. Is it clear? So how many address lines are connected to both of them? Only 14 address lines. Only 14 address lines are connected. So that's why I have to make a separation line among them. A0 to A13. These are varied from all zeros to all ones. Only these are connected to both of them. That's why these are varied. But those 2 remaining address line, these cannot be varied because these are not connected to anyone else. It is only available with microprocessor. শুধু যদি মাইক্রোপ্রসেসরের সাথেই আমার যদি এই কানেকশনটা থাকে তাহলে তো এটাকে ভ্যারি করার তো জায়গা নেই কোথাও। ঠিক আছে, ভ্যারি কখন হবে? যখন দুটোর সাথে আমার কানেক্ট আছে সেই ভ্যারি। তো যদি আমার কোনো ভ্যারিয়েশন না থাকে, দ্যাট উইল বি রিমেন সেম ফ্রম দ্য ইনিশিয়াল পজিশন টু দ্য লাস্ট ওয়ান। তার জন্যই যে কোনো একটা অ্যাড্রেস যখনই আমার প্রবলেম স্টেটমেন্টের মধ্যে দেওয়া থাকবে, আইদার স্টার্টিং অ্যাড্রেস অর এন্ডিং অ্যাড্রেস, আই মাস্ট convert it into a binary form and write it down every bits in this way. Okay, then make this separation line. Then this will be varied from all zeros to all ones, only those which are connected to both of them, and remaining address lines will be remain same as it was from the initial position to the last one. It cannot be varied. Okay, clear?
তাহলে চিপের সঙ্গে কানেক্টেড থাকবে না তো ওই দুটো অ্যাড্রেস লাইন?
এই দুটো অ্যাড্রেস লাইন ডাইরেক্টলি চিপের, হ্যাঁ এটা এই অ্যাড্রেস লাইন তো চিপে তো নেই আর।
হ্যাঁ হ্যাঁ
ঠিক আছে, হ্যাঁ ঠিক আছে। তো এই দুটোকে আমি ওপেন করে রাখতে পারি না। কোনো ওয়্যার কোনো ডিভাইসের কি দেখেছো যে ওপেন আছে? ওপেন থাকতে পারে না। ঠিক আছে, সো ইউ হ্যাভ টু কানেক্ট ইন সাচ ওয়ে, or you have to used this address line in such way that these are not left open. আর কিভাবে সেটা করা হয় I will discuss after this. Okay, now tell me clear up to this much. Anyone have any doubt? Do you have any confusion? Anyone?
No, sir, clear.
Okay, so this is called the memory mapping technique. Okay, this table is called memory mapping. Now this concept is to be converted into a diagram format. Okay, and what will be the diagram? Look at this diagram. This is the interfacing diagram where on the left hand side is your processor 8085, on the right hand side it is the EPROM device. Okay, 16K cross 8 EPROM. Now it has 14 address line. That's why from A0 to A13 these are connected to both of them, and it is 14 address lines. Now it has 8-bit data bus. It has 8-bit data bus from D0 to D7. Both are connected in this way. Now the remaining address line, which is A14 and A15, these are used to enable this IC, because these are the hands and legs, but this is the actual uh, signal, because without enable this IC no read operation can be performed. কোন একটা ডিভাইসকে আগে প্রথমে অ্যাক্টিভ করতে হয়, ঠিক আছে, তারপরে সেটাকে দিয়ে তুমি কাজে লাগাতে পারো। and how can you active or how can you enable this device? Using the chip enable signal, or some device, maybe it is represented by CS bar, chip select signal. Also both are same, only it depends on the manufacturer of that device how they can be represented, these signals, either CE bar or CS bar, both are same, chip enable pin or chip select pin. Now this chip enable signal is to be processed by the help of the two extra remaining address lines. Now here, what is the status bits of these two lines? 1 1 means both are high always, from the initial to the last one both are high. So you need this signal as low, but your inputs are high. So if you connect an NAND gate, if you connect a NAND gate circuit, then the inputs of these NAND gates will be high. At that time the output will be low. So output will be high, output will be low if both the inputs, if all the inputs of that NAND gate is high. Only in that condition the output will be low, and your low output is needed to connect the C bar signal, because it's a low level signal. Clear? So if these are 1 1, you have to make it 0 by the help of this NAND gate, and that 0 should be connected to the CE bar pin of that memory device, so that it will be enabled. And after enable this, the output signal, which is the actual control signal, that signal should be connected to the memory read control signal of the microprocessor. And when this control signal is given, the required number of data can be fetched through this data bus, and it is received by the microprocessor using its data bus. Okay, so first microprocessor gives the address through these address lines. When this device receives these address lines, after that microprocessor enable this IC. When it is enabled, microprocessor gives the control signal to that IC, and when this IC receives this control signal, it gives the data over here, and microprocessor reads the data through this data bus. In this way the operation is every operation has to be completed. Okay, read operation. Is it okay? Any confusion?
No, sir.
Anyone else?
No, sir, clear.
So in your exam, if this type of statement is there, interface 27128 EPROM whose size is 16K cross 8 IC with the 8085 such that the starting address is assigned to the chip is this one, you have to just consider this memory mapping table so that you can calculate the ending address if starting address is given in your problem statement, or if if ending address is given, then you have to calculate the starting address using this memory mapping diagram. Okay, you don't need to write these type of things. You just draw this memory mapping table, then draw this diagram from the memory mapping table, and you will get the full marks. Okay, don't need to give or write anything else after that. Only you need to consider it. That means the 16K, like this first line which is written over here, if it is given 16K cross 8, you have to write down that 16K which is equal to 2 to the power 14, so that 14 address lines are required from A0 to A13. That's all. Okay, after that you have to draw this memory mapping table, then draw this interfacing diagram. That's it. Okay, so that's all for today. If you have any confusion, you can ask me now.
Sir,
Yes.
sir, all these things were clear, sir. Just one clarification, sir. So, would you kindly explain that 16K is equals to 2 raised to power 14 part once again?
Yes.
That was a little bit confused.
Okay. Wait a minute. Okay. We know that 1K, 1 KB, which is equivalent to 2 to the power 10. Are you familiar with this term? 2 to the power 10
Yes, sir. Yes,
equals
sir.
to
Yes,
1
sir.
KB.
Yes, sir. Now, sir, it's clear. Then, as it is
Uh,
16, sir, therefore it will be 2
yes.
into
So
4.
that
Yes, sir.
means 2
Yes, sir.
KB means 2 KB.
2 into 2 raised to power 11, sir. Yes, sir.
Yes. Yes. Okay. So 2 to the power 11.
Yes, sir.
So in this way, 4 KB means 2 to the power 12, 8 KB means 2 to
12
the power 13, and 16 KB means 2 to the power
to the power 14.
14.
Yes,
Okay.
yes,
So
yes.
always remember.
Nice.
So always remember this thing, so that you can calculate any size. Okay, whether it's 2 KB or 16 KB or 64 KB, whatever. Okay. So 2 to the power 10 equals to 1 KB. Okay.
Yes.
Anything